Okay, I'll get started. Hope you can hear me clearly. Just a final reminder that this Thursday's class is test number 1. I have published a Canvas practice test for you to take a look at. It has the format, the style of the real test that you'll be working through. So there are 6 multiple choice, 9 numerical answer, and 1 fully worked out problem on the practice test. It covers all this material that we've covered from the beginning of the semester through today's class. So it's electric charge, forces, fields, flux, potential, theoretical underpinnings of electricity, and then it's applications to electrical circuits with resistors, capacitors, batteries, and solving electrical circuits. So that's the material that we're covering. The test, you'll call into lecture class like regular. Will be on Zoom for the test. You can use your notes, you can use your book. You cannot use internet resources, so you can't Google things, and you'll have your formula sheet. Any questions on all that before I get on with the actual lecture class?
I have a question about the fully worked out problem that we'll be submitting. Will it be like within the test itself, or will there be like a separate assignment we have to go and externally submit that to?
So the fully worked out problem is in the test itself. So it's the last question. If you take a look in the practice exam, you should see it. You'll see it's the last question of the test, and it's one where you can upload or submit a PDF or a JPEG. Does that make sense?
Yes, thank you very much.
Can we access homework problems on WebAssign during the test? So no, you cannot use other than the test, do not use internet resources. So don't use the homework problems. You can use your notes, you can use the textbook, you can use the formula sheet, but not internet resources. Hope that answers that question. That was actually a good point. I should make that clear. Any other questions? Will the solutions to the practice test be published on Canvas? Yeah, I will have posted this afternoon my solutions of the test. That's where I'm making a video and I'll just record me working through the test, and that will get published later this afternoon. If you have a textbook online, is it okay to have that open? I guess that's a good point. I hadn't thought about that possibility. I think that's only fair that if you've only got an online textbook, then you could use that online resource. Does this mean that the submitted work out problem needs to be done on paper only? Yeah, so you don't need to print anything out, but you need to write out your solution and you need to upload your solution as a PDF or a JPEG. So this is just like you've been doing the recitation problems, where you will write your solution out and you'll upload those. If your notes are on OneNote, I think that you can use your OneNote notes as well. I hadn't thought about that possibility either. What I do not want you to do is to obviously Google solutions to problems, or Google how to solve problems. If you're looking up the textbook, that's in the spirit of the class, right? It's open book. If you're looking at your notes, that's in the spirit of the class. You're allowed to use your notes. So those things are fine. Okay, then let me get on with today's material. So in today's class, I want to continue some work we were doing in the last class. In the last class, we were solving some circuits with series and parallel resistors. I want to continue solving some circuits with series and parallel resistors. They're going to be a little trickier circuits that we're solving with parallel and series resistors today. So that'll be the first chunk or first part of the class. If we got time, I'll also talk about circuits with batteries, resistors, and capacitors. And if we don't get time, I won't talk about circuits with batteries, resistors, and capacitors. And that section would not be on the exam. So there's one final section on today's class that covers batteries, resistors, and capacitors. And until I see how far I get in today's class, I don't know whether it's going to potentially be on the exam or not on the exam. Okay, so let's look at some example problems involving, or let's look at an example problem involving an electrical circuit that actually has components of the electrical circuit that have resistors in parallel and other components that have resistors in series. So it's this circuit here. Let me get my pen going. So this is a circuit that has components where resistors are in series. For example, here, the 5 ohm and the 20 ohm resistor are in series. And then it has components where resistors are in parallel. Obviously, this 10 ohm is in parallel with this 5 ohm resistor. So how do we solve a circuit where we've got bits or pieces of it that have parallel and series resistors, when the rules we met last class were circuits that were either completely parallel or completely in series? So we're going to see how to do that. And it's not too hard to do that. It's relatively straightforward to do that. Okay, so the problem, actually, I should mention the question, shouldn't I? Let me just go back. This problem, we're going to do two things. We're going to find the equivalent resistance for the entire circuit, which is made up of these 5 resistors. And then once we found the equivalent resistance for the entire circuit of 5 resistors, we'll actually look at an example of calculating some detail about the circuit. I'm actually going to calculate the electrical potential between this terminal A at the bottom here and this terminal B at the top here. And that could be a proxy for calculating many things about the electrical circuit. I could be calculating the voltage across the 10 ohm resistor over here on the far left, or I could be calculating the current through the 5 ohm resistor over here on the far right. So I'm trying to show you how you would go about this sort of calculation in general. And the starting point is typically figuring out the equivalent resistance. And then once you got the equivalent resistance, it's kind of the platform or the stage from which you can jump off into the details of the circuit and figure out, solve other pieces of the circuit, currents, voltages, powers, etc. Okay, so here I'm solving the equivalent resistance of the entire circuit. So the single resistor that I could replace the 5 resistors with, and for the same applied voltage, draw the same current. And we find that equivalent resistors actually in a series of steps. We're going to work our way from A, which is the original circuit, through B, through C to D, which is the final circuit that contains just a single equivalent resistor. So up at the top, that's the circuit from the prior slide with all the individual resistors. Down at the bottom, that's the circuit where we've ultimately replaced everything with a single equivalent resistor. And so let's see how we get there. And basically, we get there by spotting bits and pieces of the circuit that are simply parallel resistors or series resistors, and replacing those simply parallel resistors with their equivalent resistance, or replacing those simply series resistors with their equivalent resistance. And so that's where I started upstairs here. See in these 2 resistors here. These 2 resistors here, they're labeled resistor 4 and resistor 5. They are just in series with one another. An electron going around this branch of the circuit has to go through R4 and has to go through R5. They are simply in series. And so I can replace this pair of resistors with their equivalent resistor. And that's the calculation I did here. So R45 is the single equivalent resistor I'm going to replace R4 and R5 with. And because they're in series, it's just R45 is just the sum of R4 and R5. And R4 is 5 ohms and R5 is 20 ohms. So we get 25 ohms. And so that's the first step that I made. And I redrew the circuit. I redrew the circuit in B, replacing the 2 resistors R4 and R5 with their equivalent resistor R45, the 25 ohm resistor. And so that's what I've got now in part B. Now I spot that my circuit contains 3 resistors over here on the left, center, and right that are simply in parallel with one another. So now I've spotted another piece of the circuit that I can use my rules for series and parallel resistors on, because these 3 resistors are simply in parallel with one another. And so I said I could replace R2, R3, R4, 5 with a single equivalent resistor based on the laws for parallel resistors. And so that was my calculation over here on the right. I called the single equivalent resistance that I'm going to replace R2, R3, and R4, 5 with, I called that R2, 3, 4, 5. Well, that's a mouthful, isn't it? But I gave it that name because I wanted to indicate that it's replacing R2, R3, and R4, 5, which was a replacement for R4 and R5. Anyway, because this is a parallel resistor network, the inverse of the equivalent resistor is the sum of the inverses of the individual ones. And I know all the individual ones, right? R2 is 10 ohms, R3 is 5 ohms, and R4, 5 is 25 ohms. I plug them all in, and I figure out that the equivalent resistor is just under 3 ohms, 2.9 ohms. Remember that parallel resistors have an equivalent resistance that's always smaller than the individual resistors. So this 2.9 ohms is smaller than any one of the individual resistors. Series resistors, on the other hand, our first set, they always have a resistance, the equivalent resistance is always larger than the individual resistors. Okay. Anyway, now Now I can replace this network of 3 parallel resistors with my single equivalent resistor. So I did that here. Here's R2, 3, 4, 5. It's 2.9 ohms, and I redrew the circuit. You see, now the circuit's starting to get simple. Now the circuit just has a 2.94 ohm resistor in parallel with a 10 ohm resistor. An electron going around this circuit has to go through both those resistors. And so finally, one last step, I can use my rules for series resistors to replace the 10 ohm resistor and the 2.94 ohm resistor with its equivalent resistance. And so that's what I did over here. That's what I did over here on the right-hand side. The equivalent resistance for the entire circuit now, so this is what this final resistor will be, is simply the sum of R1 over here on the far left, 10 ohms, R2, 3, 4, 5 over here on the far right, 2.94 ohms. So it's 12.9 ohms. And that gives me, as you see here, this final circuit where I've reduced, I mean, this is brilliant, don't you think? Maybe not. I've reduced that complicated 5 resistor parallel series circuit into just this single equivalent resistor across the terminals of the battery. So that's a really great accomplishment. Hope you like it. Okay, now we're going to answer the question that was posed. What is the potential across or between those two terminals A and B in the original circuit? And as I say, this is really just I would call it a proxy question. It's a proxy question because I could have asked any sort of question about current, voltage, or power in the original circuit at this point, and I would go at it, work it out using this concept of the equivalent resistance. I see that there's a question in chat. It's actually got answered by Lydia, but that last step where I combined R1 and R2, 3, 4, 5, they are series resistors. They are not parallel. An electron has to go through both of them. It can't avoid one of them. Okay, so let's find this potential between these 2 points A and B. That's what we're going to do here. And there's 2 little steps to this. The first thing I did was find the current that's drawn from the battery. And then the second thing I did was find the potential. And when I found the current flowing from the battery, I worked with the equivalent circuit containing just that final resistor. And when I worked out the voltage between the 2 points A and B, I actually work with not the original circuit, not the very final circuit, but circuit C, where we had got down to 2 resistors. Because in that circuit, it isolates the potential across the A and B. It allows me to solve that potential across A and B. Okay, so let's find that. Firstly, let's find this current that's coming out of the battery, and then let's find this potential that's either, you can think of it as across this combination of resistors. We're going to do those 2 things. Firstly, this current is flowing around the entire circuit. So I can just use Ohm's law. The battery provides an EMF, a potential difference from its terminals, and that's equal to the equivalent resistance of the circuit times the current that's flowing in the circuit. I know the battery's EMF, we were told it was 25 volts. I know the equivalent resistance now is 12.9 ohms. So I can rearrange Ohm's law as an expression for the current flowing out of the battery into the entire network. and it's just going to be the battery's EMF 25 volts divided by the equivalent resistance 12.9 ohms. And if you do that calculation, it's 1.9 amps, 1.93 amps. So now we know 1.9 amps is flowing out of the battery around the entire circuit. And that means that 1.9 amps is flowing around this equivalent series circuit. Now I'm doing it. This equivalent series circuit that contains the individual resistor R1 and that equivalent resistor of resistors 2, 3, 4, and 5. Now, we know 1.93 amps comes out of the battery. That 1.93 amps is going to flow through R2, 3, 4, 5, and then it's going to flow back through R1 to the battery. So that current that we figured coming out of the battery is flowing through each of these components, the equivalent resistor on the right, the original resistor on the left. That current, according to Ohm's law, will determine the voltages across the equivalent resistor on the right and the individual resistor over here on the left. And we can use that to figure out this potential AB, because that's simply the potential across this equivalent resistor on the right. So here's my working out. The interesting voltage AB, is the voltage across this equivalent resistor. And that voltage across that equivalent resistor is the current flowing through that resistor, flowing around this circuit, times its resistance. Well, I know the current, I know the resistance, and so I've just got to multiply those and I get 5.67 volts. So what we just learned is that 5.67 volts are across this portion of the circuit, and the remainder, it will be about 19.3 volts, will be across this piece of the circuit. And so that's how the battery's EMF is subdivided between the different elements of the circuit. Anyway, that's an example illustration of a problem involving a more complicated circuit. Okay. Final topic on these sort of more complicated circuits is what's called Kirchoff's circuit rules. And so these are rules about currents and voltages in circuits, or laws about currents and voltages in circuits that, like the equivalent resistance concept, help us solve, understand electrical circuits. And it turns out that the concept of the equivalent resistance is a good tool for solving many circuits. We just solved the prior circuit with it, but it's not a tool that can solve every circuit. And we're going to look at a circuit that it does not solve. And that's where Kirchoff's circuit rules come in. And so here is a circuit, an electrical circuit, that is not reducible to a single equivalent resistor. In the last problem, we reduced the circuit to a single equivalent resistor. But in this problem, I guarantee you, there's no way you can solve this by reducing this circuit into a single equivalent resistor. And the problem is, so if you look at this circuit, how did we start the last problem? That's a good question. How did I start it? I started looking at the circuit and identifying pieces of the circuit that were just either resistors in parallel or resistors in series. So I had to find some bit of the circuit which was just parallel resistors or just series resistors. But in this circuit, there is no no part of the circuit that just looks like a pair of parallel or series resistors. Let me just give you an example, right? You might say, well, look, this 2 ohm and this 3 ohm resistor are in parallel with one another. But they're not simply in parallel with one another. There's a battery in this part of the circuit too. And that's true of any of the other arms of this circuit. You might say the 1 ohm and the 2 ohm are in parallel with one another, but they're not simply in parallel with one another. There's batteries there also. You might say that the 1 and the 3 ohm are in parallel with one another, but they're not simply in parallel with one another because there's a battery there also. And so there's no piece or part or bit of this circuit that's simply series and parallel resistors. And so our method approach of the single equivalent resistance fails. And so that's where Kirchoff's rules come in. So I'm going to introduce the rules, and then we're going to apply the rules to a particular problem. Now, I want to say something about the problem that I'm going to solve with Kirchoff's rules. The entirety of the problem, from the circuit to figuring out, say, the currents in the circuit or voltages across components of the circuit, is a pretty lengthy, complicated problem. What we're going to focus on, and what there would realistically be questions on an exam, would be how you apply Kirchoff's rules to a circuit problem like this, how you use Kirchoff's rules. And I don't think I would expect you to solve an entire circuit problem on a single exam, but just to know how to apply the rules to a circuit. You'll see what this means, I hope. Okay, so first of all, there are two rules. There's what we often call the voltage rule and what we often call the current rule. Sometimes they're called the loop rule and the junction rule. So let's look at the current or junction rule first. So this guy here. And to help us, I've drawn this circuit here, which has these 3 resistors and these 2 batteries. So the current or junction rule applies to a junction, or what we call a node in the circuit. It's where my wires meet, or terminals meet. So here on the right is a junction. There's also a junction over here on the left. We could apply it here too. And the rule is kind of simple and straightforward. It just says that the current that flows into a junction must be equal to the current that flows out of the junction. That's really just saying that the charge can't sort of pile up in the junction. Whatever is flowing in must be flowing out. Like the water that flows underneath the bridge has to flow out the other side of the bridge. The water can't pile up beneath the bridge. And same idea for the current here. The current flowing into the junction must flow out the other side of the junction. It can't pile up at the junction. So that's the basic idea. So as an example, look at the currents on this circuit. So I1, I've drawn it going towards the right. It flows into this junction. I2, I've drawn it going towards the right. It flows into this junction. I3, I've drawn it going towards the left. It flows out of that junction. So for the currents drawn, I1, I2, I3, on this particular electrical circuit, I1 and I2 flow into the node or junction on the right, and I3 flows out of that junction or node on the right. And so this is just one way here of writing the fact that the currents flowing in, which are I1 and I2, added together must be equal to the current flowing out. And that's the junction rule. So I don't think that rule's complicated. It's a basic idea. And you might be asked to think about that rule on a circuit problem on an exam, for example. Second rule is the voltage or loop rule. So this applies to a complete loop around the circuit. There are several loops around this circuit. Let me focus on this one here. It's a loop, a complete loop around the top half of the circuit. There could be another loop around the bottom half of the circuit. And there can be actually a third loop that goes right around the outside of the circuit. But to illustrate the voltage or loop rule, let's think about the loop around this top half of the circuit. The voltage or loop rule says that when you walk around a complete loop in a circuit, so any circuit, you're going to walk around a complete loop. Imagine you're a lecture. As you walk around the circuit, you're stepping up in potential, you're stepping down in potential, you're changing your potentials. After you've gone all the way around the circuit, completed your loop of the circuit, those ups and downs, if you add them all up, the net up or net down is zero. Ultimately, when you get back to where you started, the potential changes all add up to zero. And so that's the loop rule. And I've tried to illustrate it here for this loop with this equation. So let's start walking around the top circuit. So I'm going to start here in the middle of the middle arm, right in the middle of the circuit. And I'm going to walk over here towards the left, so clockwise around the circuit, and then back to that midpoint of the middle arm. And let's just see what potentials I meet. And I actually have noticed, I've noticed oh my gosh. I walked around the bottom arm of the circuit. I know I put this sketch up here, but I've walked around the bottom arm of the circuit this way. That's the rule I wrote down here. So we're going around the bottom arm of the circuit, not the top arm of the circuit. So as I start walking towards the left, okay, there's no change in potentials along the wire. I get to the far left, and then I meet the battery, right? I'm meeting this battery. And I'm walking from the negative terminal to the positive terminal, and I'm walking up a potential hill that's 4 volts. And so that's this 4. That's the first change in potential I meet. Then I continue walking across this central path here. And as I walk across here, well, I'm walking through a wire, nothing's changing in potential there, but then I meet the resistor. And when you walk through the resistor, right, there's a potential across the resistor. And so I have a change in potential when I stroll across the resistor that by Ohm's law is the resistance of the resistor times the current in the circuit. And so that's what you see here. See the 2I2. I2 is the current through that resistor. The 2 is the 2 ohms of resistance of that resistor. So 2I2 is the voltage drop change across that resistor. Now there's an important question here. Does the voltage increase or decrease? Well, positive current always runs downhill through a resistor, always runs the direction of current is always from the higher potential to the lower potential. And so since we're walking with the direction of the current, this is a negative change in potential. And so that's the minus sign here. So then we've gone through this 2 ohm resistor. I walk to the far right over here, this node that we met before, and then I will start walking back towards the left to my final location where I started, and I meet another resistor. And so again, there's going to be a potential difference across this resistor according to Ohm's law. And when I walk across this resistor, there'll be a potential difference that is given by the product of the current and the resistance of the resistor. The current is I3, so you see an I3 here. And the resistance of the resistor is 3 ohms, so you see the 3 ohms here. And again, because I'm walking in the direction indicated for the current, and current flows down the potential hill, then this is a decrease in potential. So that's why there's a minus sign here. And so these are the 3 potential differences when I walked around this bottom loop of the circuit. The battery, I climbed up in potential. The 2 ohms, I went down in potential. The 3 ohms, I went down in potential. But they all add up and must add up to 0 once I get back to where I started. And so that's the voltage rule for that lower loop. There's a question in chat. Let me look at that. How is it a loop in the top half? I thought it goes from positive to negative side of the battery. So I'm walking around, just to make this clear, my equation is for this loop. This is the loop around the bottom half of the circuit. And when I'm going clockwise around, I'm going from the negative end of the battery to the positive end of the battery. I'm like walking up a staircase from the first floor to the second floor. When I get to the 2 ohm resistor, I'm sliding down the staircase as the current, just like the current, or water would run down the staircase. And when I go through the 3 ohm resistor, again, I'm sliding down the staircase, just like the current is flowing down the staircase, or water would flow down the staircase. I hope that makes sense for those directions. So can there be a loop in the top half of the circuit? Yeah, let me make that clear. There are 3 loops, and I've just given you example 1 loop. There is a loop in the bottom half, which is where I generated the equation. So this loop. There is a loop in the top half, and there's a loop around the entire circuit. So there are 3 loops here, and we could have made 3 equations. Can you start the loop rule starting in the 5 volts? Yeah, you can start a loop rule anywhere. That's a good point. But you have to come back to where you started. So I could have picked any one of these 3 loops, the entire circuit, the bottom half, the top half. We could have started anywhere on these 3 loops, next to a resistor, next to a battery, or whatever. But you have to complete the loop. You must complete the loop so that the voltages add up to 0. I think we're going to work through an example. You'll see it maybe clearer in the example. But let me make, before we do the example, let me make a couple of important points. And it has to do with this signs, plus or minus signs of when you walk across a battery or when you walk across a resistor. So look, here's 2 examples. Top one, oops, sorry. Top one, I'm going to walk across a battery in the direction of this arrow here, from the negative to the positive terminal. Bottom one, again, I'm walking to the right across the battery, but I'm going from the positive terminal to the negative terminal. The battery's reversed. So I just want to make clear that in the top case, we're climbing up the potential hill in the battery from the negative to the positive terminal. And so if the battery is 3 volts, the change in potential in Kirchoff's loop rule, voltage rule, is plus 3 volts. When I walk across the battery in the bottom circuit, I'm traversing the battery from the positive terminal to the negative terminal. So it's like I'm walking down the stairs. Then the change in potential is minus 3 volts. And getting the signs right, getting the signs correct is very important in Kirchoff's rules. And so that's the signs for a battery. That's probably the easier one. What about a resistor? So here's the 2 cases for a resistor. Again, when you walk across a resistor, there's a change in potential given by Ohm's law, product of current and resistance. But it's important to get the sign of the change in potential, whether you went up in potential or you went down in potential, correct. And so these are the 2 examples here. Upstairs here, the current through this resistor is flowing from left to right. And downstairs here, the indicated current is flowing from right to left. So upstairs here, I'm walking in the direction indicated of the current flow. Downstairs here, I'm walking in the direction opposite the current flow. Now, current is flowing down the potential hill, like water, it would flow down the staircase. And so walking in the top sketch here, in the direction of the current, that means I'm going down the potential hill. And so my change in potential is negative. It's negative IR, size of current times the resistance. In the bottom case, right, I'm walking opposite the direction of the current. Current's flowing downhill, I'm walking uphill. So this change in potential is positive IR. And so that's the signs of the potential change when you walk across resistors. That's important. Okay, so let's look at an example of solving a circuit with Kirchoff's rules. And here's the circuit that I want to solve. So this is an example of applying Kirchoff's rules. And here's the electrical circuit. And it's got these 2 batteries, and it's got these 3 resistors. And this is an example of a circuit where you can't break it down into a single equivalent resistance, because you can't isolate, for example, pairs of parallel, pairs of series resistors. There's a question in the chat about, with the loop rule, what direction do you go? Do you go clockwise or counterclockwise? You can go either direction. There's no rule about what direction you have to go. So you can go clockwise or you can go counterclockwise. The rule is that depending on which direction you're going to go, the changes in potential as you walk across circuit elements would be opposite if you went the opposite direction. So you have to get the signs of the potential changes right, but you can walk either clockwise or counterclockwise. So that's a good question. So what we're going to do with this circuit is calculate you see there's 3 arms in this circuit. There's the top, the middle, and the bottom. We're going to calculate the 3 currents flowing in those 3 arms. That's our goal here. And so I redrew the circuit here, making things a little bit clearer, maybe, or maybe not, maybe just a little bit bigger. But this is the circuit that we want to solve. And we want to find these three currents flowing through these three arms on this circuit. So the first thing I did was, and this is an important thing, or this is an important point, is you have to, in applying Kirchoff's rules, you have to pick directions for the flow of the current through the arms of the circuit, because you need to have directions for the flow of the current through the arms of the circuit to be able to know whether as you walk across the resistor, whether you're going up or down a potential hill. So you need to know, you need to have directions for the currents. And what you actually do is guess the directions of the currents. So we're just going to guess the directions of the currents. Now, when you apply the rules and solve the circuit, if you guessed wrong for the directions of the currents, you would get negative values for the currents. It wouldn't change the answers to the circuit problem. You get the right currents, but you just get minus signs indicating that your arrows indicating the directions of the currents were in the wrong direction. So you have to guess the direction of the currents, but you can guess them right or guess them wrong. You're still going to get the right answer for the circuit problem, as long as you stick with those guesses and be consistent, entirely consistent with those guesses. So that's what I'm doing here. I'm just guessing and labeling the three currents in the three arms of the circuit. And look, in each case, I1 is thrown through the top half of the circuit, top arm of the circuit. I guessed it's going from left to right. I2 is going through the central portion of the circuit. I also guessed it's going from left to right. And I3, because I know that, you know, I can only have two currents come out of this node. Oops. I need some current to flow back into that node. I guessed I3 to be flowing into that node, i.e. the opposite direction from right to left in the circuit. But it is just a guess. And I actually write down now, I can't remember whether I got these guesses right or I got these guesses wrong. We'll find out. But we're going to use these guesses on this slide, because on this slide, I'm indicating the signs of the positive and negative ends of the batteries, which are obvious, but the positive and negative ends of the resistors, which are based on the directions of these currents. So importantly, right, to get these signs right, we've got to remember that this short arm is the negative terminal, and this long arm is the positive terminal of the battery. And so if we walk from left to right across these batteries, we're going to go up in potential. If we walk from right to left, we're going to go down in potential. For the top two resistors here, the currents are flowing towards the right. So these currents are going downhill. And so if you walk in the direction of the current, you're going down the potential hill. If you were walking opposite the direction of the current, you'd be going up the potential hill. So over here on the left of the top two resistors is the more positive end of the resistor, and over here on the right is the more negative end of the resistor. The current in the bottom arm of the circuit is in the opposite direction. And so again, it's flowing down the potential hill. So that means that for the bottom resistor, the right-hand side is the more positive potential. The left-hand side is the more negative potential. So walking towards the left here is down the potential hill. Walking towards the right would be up the potential hill. And so this is an important slide, I think, about the direction, the signs of changes in potential when you walk across batteries, signs of changes in potential when you walk across resistors. And it's important to get these signs right. There's a question in chat. So my currents, we always draw in circuit diagrams conventional currents, the direction that positive charges would flow in. That's the direction of the current. It may or may not be electrons in a circuit, but it doesn't matter whether it is or is not electrons. We always draw the currents, the direction that positive charges will flow. And so they always flow down the electrical potential hill. Okay, so these are the signs. So now let's construct some equations. And so that's what I'm doing on this slide. I've got three unknowns in this problem. This is why I say this is not only a complicated circuit problem in terms of some of the ideas, Kirchoff's rules, but it actually can be a mathematically complicated circuit problem because you've got three unknown currents, and you're going to have three equations to solve three unknown currents. But I want to focus on setting up the equations based on Kirchoff's rules. Okay, so I'm going to apply Kirchoff's current voltage rules. The easier one to apply is typically the current junction rule. So I'm going to pick this junction over here on the left. I could have picked this junction over here on the right, but I'm going to pick the one over here on the left. And, you know, again, that's another choice I'm making in solving this problem. This type of Kirchoff's rule problem is filled with all these choices you make. And I know that, you know, if you're like me, you start to get anxious and nervous about these choices, but they are choices that you and I can make differently. They are choices that, as long as you're consistent with the signs, we'll all get the right answer. So I chose this junction, and I said, look, I2 and I1 are both flowing out of it. The arrows come out of it. I3 is flowing into it. And so the current in must equal the current out. That equation here. There's different ways we could write that, but it says current in equals current out. So that was one equation. That's the current or junction rule. So I hope that was easy enough, straightforward enough. Now let's start applying the voltage rules. And I applied them twice to get two more equations. And so let's look at the two equations I got. In the first equation, so we've done this one, but in the first voltage or loop equation is this one here in the center. So for that one, I actually walked around this. What loop did I walk around? I'm trying to check that right now. I think I walked around this this bottom loop, this loop here, to make this equation here. And so I started at the midpoint of the bottom arm, and I start walking clockwise around the circuit. And as I walk, no, actually I'm not walking around this one. I'm getting this wrong all the time. I'm walking around the big circuit. As I walk around the big circuit, I first meet this, oh no, I'm getting that wrong again. No, I'm walking around the bottom circuit, sorry. Walking around the bottom circuit, and I meet this battery number 2. And I'm going from the negative terminal to the positive terminal. So I'm going up in potential, and I'm going up by 10 volts. So that's this piece here. I continue on around the circuit. I pass through resistor number 2. And the potential difference across resistor number 2 is I2R2. And that potential difference across that resistor, well, it's a decrease in potential because I'm walking in the direction of the current flow. And so that's negative I2R2. And then finally, I come back down through here, and I walk through the bottom resistor, that's R3. And as I walk through the bottom resistor, again, the potential drop change is the current in that resistor, I3, times the resistance of that resistor, R3. And again, I'm walking in the direction of the current flow. It's flowing from right to left here. And so that is a decrease in potential. And so that's that term. So those are the three changes in potential as I walk around the bottom loop. And those three changes in potential add up to make no net change in potential when I come back to where I started. And then this final equation here, I won't go through all the details of it, because it's the same idea. It's when I walked around the entire loop. So if you walk around the entire loop, I go through battery 1, resistor 1, and resistor 3. And so you see a contribution from battery 1, resistor 1, and resistor 3. And you see these three changes in electrical potential must add up to 0 once you get back to where you started, walking around that current loop. And so this is how you construct equations that describe the circuit using Kirchoff's rules. And it's basically these two rules. Think of a node, current flowing in must be the current flowing out. That's this, the first equation that we came up with here. And then think about loops. The voltage changes around a loop must add up to 0 if you complete the loop. That's the second equation and the third equation here. And from the mathematical perspective here, we've now made three equations. Those three equations have three unknowns in them, the three currents, I1, I2, I3. And so this has turned this problem into a mathematical problem of solving the three equations for the three unknowns. I'm going to, on the next two slides, solve those three equations for the three unknowns. I'm going to go through it fairly quickly because I wouldn't ask you to solve three equations for three unknowns on a test. I would ask you perhaps to set up a Kirchoff rule equation for a node in a circuit, or a Kirchoff rule equation for a loop in a circuit, or Kirchoff rule equations that describe the circuit. But I wouldn't on a test ask you to solve three equations, three unknowns, because it's too time consuming. Let's look at how it works. Okay, so this is a slide with a lot of equations on it, but let me explain what I'm doing here. Starting at the top, I've just reproduced the three equations. Starting at the top, I just reproduced the three equations from the previous slide that we got with Kirchoff's rules, Kirchoff's current rules, Kirchoff's voltage rules. That is something we should be able to do. I then have done two things, basically. I've filled in the numerical values for the batteries and for the resistors. So I know all the resistance of the resistors. I know all the EMFs of the batteries. And so I fill in those numbers. Now, normally in a problem, you don't kind of fill in the numbers to get towards the final equation. But actually in Kirchoff's rules, we tend to fill in the numbers early on because it's easier to handle three equations, three unknowns with the numbers rather than the three equations, three unknowns with lots of different symbols. So it's a special case. Normally I wouldn't put, as you know, I wouldn't put the numbers in equations early on. I wait to the final equation. The exception to the rule, Kirchoff's rules, I put the numbers in early on because it simplifies the three equations for the three unknowns. So I put in the numbers. Actually, that was the step in the middle. put in 10 volts, 20 volts for the 2 batteries. I put in 5, 20, and 30 ohms for the 3 resistors. So that was the middle step. And then I just simplified the equations a little bit. So the only simplification I made was that, you notice in the middle equation here, 5, 10, 20 are the coefficients. Notice in the bottom equation here, 20, 30, 20 are the coefficients. Well, look, I can divide the middle equation by 5 and simplify it. I can divide this bottom equation by 10 and simplify it. And so I did that. And so nothing much went on in this overhead other than rearranging equations where I've stuck in the voltages, I've stuck in the resistances, and I've simplified by dividing through by common factors the equations. So I just turned my 3 equations, 3 unknowns, into 3 simpler equations with 3 unknowns. I1, I2, I3. We got to find out what they are. Okay, so how do we find out what they are? That's this slide here. Here are my 3 equations. Gosh, if I do that one more time. Here are my 3 equations, 3 unknowns, where I've stuck in the numbers. So let me just say in words how I solved them. The top equation here says that I1 plus I2 equals I3. So that equation contains all the unknowns in it, I1, I2, and I3. The second equation contains I2 and I3. The third equation contains I1 and I3. So what I did was I used the second equation to replace the I2 with I3. And then I used the third equation to replace the I3s with I1s. And that gives you an equation that just contains I1. So that's the magic of solving these 3 equations with 3 unknowns. So again, the top equation contains all 3 unknown currents. But I can eliminate I2 with the second equation, and I can eliminate I3 with the third equation, leaving a new equation that just has I1s in it. And that, if you solve that equation, you find that I1 is 0.35 amps. And then once you know I1, right, you can solve for I3 from this equation. You'll find that's 0.47 amps. And once you know I3, you can solve I2 from the second equation. Find it's 0.12 amps. And so that's the mathematics of solving those 3 equations for 3 unknowns. I wanted to show you it to make the story complete, but you wouldn't be asked to do that on an exam. So look, let me step back from that problem. That was a complicated circuit problem. It introduced us to Kirchoff's rules, the voltage rule and the current rule, or the loop rule and the junction rule. We applied to that complicated circuit with those 3 arms and 3 unknown currents, the Kirchoff's rules. We generated from the junction rule and the loop rule 3 equations containing the 3 unknown currents. And then we were, with mathematics, with algebra, able to solve the 3 equations for the 3 unknown currents. And so now we know the currents. And we know, in a sense, we now know the entire circuit. We know how the circuit is functioning. We know how the circuit is working. And so that's a big achievement. Okay. Look, this class has all been about those two circuit problems. The first complicated circuit where we use the single equivalent resistor as a tool for solving the circuit. And this circuit problem where we've used Kirchoff's rules as a tool for solving the circuit. And so the goal of those two problems was to introduce to you those two important methods. And that's how we solve, those methods are how we solve electrical circuits. I think I got a quiz question coming up. Here's the lecture quiz. And you see a circuit, and it's got various nodes in this circuit. Here's a node or a junction, various junctions in the circuit. It's got several different arms in the circuit. There's a bottom arm, a middle arm, and a top arm. And the question is, what is the relationship between the currents I1, I2, and I24? So what is the relationship between those currents? And so I'm going to write down those relationships. Now, this is an example of Kirchoff's rule, that the current flowing into a node is equal to the current flowing out of a node. So if we look at this, this diagram, right, I've got a current I2 that's flowing in and a current I1 and a current I24 that are flowing out. So there's two currents flowing in, one current flowing in and two currents flowing out. And so one answer to this problem will be that the current flowing in I2 equals the current I1 plus I24 that are flowing out. And so that's a correct answer to this problem. But there's lots of ways you could write the answer to this problem. And that was kind of the purpose of this problem. So you could also write it that I2 minus I1 minus I24 add up to 0, right? That's a way of writing it in which the currents flowing in have a plus sign, currents flowing out have a minus sign. So again, the net current in or out must add up to 0. And so that would be a perfectly correct answer to this problem. And so too would be this sum of the currents, right? Minus I2, sorry, this should be I1. Minus I2 plus I1 plus I24. Again, that's an equivalent equation. All of these are the same relationship between the currents. And so all of these are valid answers to the problem. And so I was wanting to illustrate there's different ways that you can, like different ways you can write the voltage rules, there's different ways you can write the current rules.